In this example, we are going to draw the Bode plot of function g of s. This function has a real zero, a real pole, and a complex pole. Let's start by writing this equation in the standard form needed for Bode plot. We can start by factoring 0.5 in the numerator, then factoring 2 in the first pole, and now let's look at the complex pole. The complex pole already has the standard form for this part here, where we have s over 8. 8 is clearly the cutoff frequency. So we can write s over 8 squared. So if the cutoff frequency is 8, now we need s to be divided by 8. That's the standard form. How do you make 8 appear in the denominator? Well, multiply it by 8 and also divide it by 8 plus 1. Now we can factor out 2 here. So we have 4 times 0.5 times 2 times s over 2 plus 1 divided by, now I factor out 0.5. 0.5 times 2 is 1. So we have s over 0.5 times now s over 8 all squared plus 0.4s plus 1. The result of this multiplication here is 4. So now we can see a cutoff frequency of 2 radians per second. For this 0, cutoff frequency of 0.5 radians per second for this pole. I forgot to write plus 1 here. And a cutoff frequency at 8 radians per second for the complex pole. For the complex pole, we know that a 2 zeta equals to 0.4, zeta equals to 0.2. Zeta is less than 0.5, the damping ratio is less than 0.5, so at 8 radians per second, the Bode plot will go up, and will go up by 20 log, negative 20 log of 2 zeta, which is 0.4. This is equal to plus 7.95. Now that you have all the elements, you can start to draft the Bode plot. If you go to very low frequencies, the only thing acting on the Bode plot is this gain of 4. We have no poles or zeros at the origin. So the Bode plot will start at 20 log of 4. 20 log of 4 is approximately 12. The Bode plot will start at 12. And we will stay at 12, because you have a constant gain, up to the first cutoff frequency, which happens to be 0.5 radians per second, so around here. At 0.5 radians per second, we cross the cutoff frequency of a real pole. Now the Bode plot will start to go down. It goes down by negative 20 decibels per decade. We are dealing with this pole here, which means that when you reach 50, we should be at negative 8 decibels, 12 minus 20. The problem is that in the way we have another cutoff frequency, this cutoff frequency of 2. What is the magnitude at 2? We know that from 0.5 to 2, we should follow a slope of negative 20 decibels per decade. At 0.5, we are at 12. And at 2, we will be at 12 minus 20 log of 2 over 0.5. Destination frequency and the current frequency. And this is approximately 0. So at 2, we should be at around 0 decibels. Now when you reach 2 radians per second, we encounter another cutoff frequency. This cutoff frequency comes from this 0 here. The slope that was negative 20 dB per decade because of this pole now becomes 20 negative dB per decade plus 20 dB per decade because of the 0. And will now stay at 0. and it will stay at 0 up to the next cutoff frequency, which is at 8 radians per second. At 8 radians per second, we now have a complex pole. The complex pole has a damping ratio of less than 0.5, and it will now go up by 7.95 dB. So we should go up like that, and this magnitude here is negative 20 log of 2 zeta, which is plus 7.95. So this value here, because we're starting at 0, is 7.95. Now, past this cutoff frequency at 8, we are to the left of a complex pole. The complex pole will make the slope negative 40 decibels per decade. Again, this is very similar to having two real poles at 8, with the exception of this part exactly at the cutoff frequency. Each of these poles will add negative 20 because we have two. We have always a complex conjugate is always in pairs. The slope is negative 40 decibels per decade. So we are leaving here at 0. So we end up to 7.95, back to 0. And then from 0, we go negative 40 dB. So we should be roughly around here, which is the value there, 0 minus 40, which is negative 40 decibels. This is a slope of negative 40 dB per decade. Now let's look at the phase. From very low frequencies up to the first cutoff frequency, we only have the gain acting. The gain has a phase of 0. At 0.5, we encounter a 0, a pole. The pole adds negative 90 degrees. And this goes at negative 90 up to the next cutoff frequency, 2 radians per second coming from the 0 plus 90 degrees. Keeps at 0 up to the next cutoff frequency, which is 8. 8 comes from a complex pole. So the complex pole adds negative 180 degrees. And this will stay at negative 180 as now the frequency tends to infinity. You can attempt to interpolate this. Something like that. Passing by 45, 45, and 45, negative 45, and then tending to negative 180 degrees as the frequency tends to infinity.